I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism Podcast, an exploration of the past, present, and future of material science. And we are back with another episode in our quantum materials mini-series. Can I just say really quickly, if you're the type of person that bails halfway through or when it gets close to the end, don't this time, because this episode is brought to you by the American Ceramic Society, and they have a special, really cool offer just for our listeners. It's going to save you some money on some really cool online courses that they're offering. And we're joined by none other than one of the most entertaining speakers I've ever seen at a conference, Paul Canfield from Ames Laboratory, also an appointment at Iowa State University in the physics department. Paul, how are you doing?
Doing well. Thank you so much. I don't recognize myself from the introduction, but hopefully I'll find myself soon.
Absolutely. Well, we're super excited to have you here. Somebody recommended you as a sort of definitive voice in talking about quantum materials. And a key part of that is new materials, right? You can't get new phenomenon from the same old materials. Or if you can, it's going to be boring. I think you had a quote in one of your papers about sort of, you could do everything in silicon, but what's the point in that, right? Where's the variety in that? So if we're going to be finding new materials, today's whole episode is crafted around the discovery of new materials in that process. Okay. So you've written a number of really cool sort of perspective pieces on discovering new materials, and you should know you've done some really great work in actually finding new materials, and you've compared it to a number of different things. So we're going to go through a couple of these because they're really fun comparisons. And your first one is cooking. So I got to ask first off, are you a big cook? Do you love cooking? It clearly comes through in this paper.
Oh, yeah. I've been doing it since I was a sophomore in undergraduate. Basically, first to feed yourself, but then it's the perfect way to interact with people. It's the perfect way to have a date that isn't a date. It's the perfect way to just sort of start conversations. And in the article I wrote, A Cook's Tale, it really was exploring the similarities in the same way that if you've cooked forever, you know that nutmeg will bring out the flavor in a white sauce. If you've grown materials forever, you can make educated guesses. Oh, I bet I could pull that out of tin, or I bet I could pull that out of a binary eutectic by adding a third element. And in a similar way, a nice dinner party, especially if you have friends over who are not shy, if you're testing a new recipe, you want to hear, does this work? Should I have had more cinnamon, less cinnamon, more pepper, a little chocolate, whatever? In the same way, if you're sharing a new material, oh, wow, it would probably show quantum oscillations better if it had less impurity scattering. If we can electron or hole dope it, I bet we can bring this feature to the Fermi surface. Oh my God, this requires isotopic substitution. Do you think you can do it? All of these are the same sorts of interactions played out over a somewhat longer time scale, but it's a chance to share something new with your friends or colleagues. And, in many cases, I consider colleagues friends. I have a few colleagues who I don't, and, we know who they are. We put up with them. But most of the ones that, I do long-term collaborations with are people I enjoy working with. So, yeah, it's a mixture of science and social, but cooking is a wonderful analogy. We can pursue it.
I love the idea of quality ingredients, of sharing
Absolutely.
recipes, of,
Yep.
In the cooking world, sometimes they keep things secret, but I love that you point out, that shouldn't be the case in science. Like,
that
it should
be the case in science.
You want everyone to have the best sort of outcome.
Just like cooking too, over time you start to develop a gut feeling for different things that could mix.
Absolutely.
And you begin to develop an underlying intuition that can guide your experimentation and recipes. And it is worth noting, there's a lot of overlap, or there's some sort of Venn diagram between people who are materials focused and people who like to cook. Because it seems like everywhere I go or and I talk to people who are in materials, there's usually some interest in cooking that comes along with it.
You got to be careful there. I've had grad students coming from cultures where men do not cook,
Oh,
and
really?
I've had to break them, or I become an ally of their wife. Of okay, I'm teaching dude to cook in the lab. Shall I give him some homework? What type of food do you like? There was one woman who really liked Italian, so I gave my grad student homeworks of trying this, trying that, and I would get feedback from his wife. But in terms of ingredients, one of the ones I'm currently quite obsessed with is a fantastically smoky paprika from Madrid. Madrid's one of my favorite cities in the world. It's a collection of barrios rather than a capital city, and I know Mercado Maravillas. I can go to the exact spice stall and get smoky paprika there. I'm now bringing home kilos of it because I've got so many colleagues here who are hooked on it. It's the go-to ingredient for almost anything. It's just a miracle. And in the same way, certain elements. Look, I'm at Ames Lab. We make the world's highest purity metallic rare earths, and sometimes that really matters. I remember during work on the rare earth nickel borocarbide materials. This was in the mid 90s. I could look at people's allegedly non-magnetic lutetium or yttrium, and if they had anisotropic susceptibility, I could identify which moment-bearing rare earth they had as impurity because it shows up.
This reminds me, like, people that are sort of lazy will just run to the local grocery store, whatever's nearest, right, to pick up their ingredients. And sometimes it's worth it to head over to, your bespoke sort of, organic food shop. And sometimes it isn't. And over the years, I guess you've just learned when it's worth it to pay the premium for the ultra high purity or morphology or whatever it is about the material that gives you the better properties. But you don't always know that at first hand. You kind of have to fail a few times and realize that it starts to matter, right? In these papers, hopefully you're
Well,
pointing out as a reviewer saying, like, I think this is what's going on. And you're giving this insight to them saying, maybe it was a materials issue at the start.
sure. I mean, when you discover a material, when you're first looking at it, you have to listen to what it has to say. And one of the things I try to teach students, postdocs, friends, is when you open a growth, there's a period when you should just absorb what you're looking at. If you've got shiny, beautiful facets, enjoy that for the moment of Zen. But also, look at it like a mineral sample. Geology is telling you a story. If this crystal grew on that, or if you have dendrites here, or certain angles, these are all giving you hints. And then when you start doing the first basic measurements, you can get hints. But I did want to go back to something that went whizzing by, and I want to get on a soapbox.
Oh, let's hear it.
Okay? All right. You do have lots of groups, and perhaps more so in physics and chemistry, that want to hide the details of how things were grown. I remember, look, we had the first published papers on MGB2. We figured out how to grow it. We confirmed superconductivity. I didn't want to claim the discovery, so I contacted Akamitsu and urged him to give me some reference. But we published in that first paper exactly how to make high purity MGB2. And it's something my group does a lot. We teach the world, but then I had people saying, God, you're an idiot. You lost a month or two of time when you would own this and no one else could do it. And it comes at a cost, but it's what I was taught the scientific method is. But I would encourage any of your listeners who might happen to be a referee, if details are not given adequately about how to make it,
It's not reproducible. That's not
chuck it.
science.
It's not science. It has to be there. So there we are. But one of the other things that bothers me then is we teach the world, but then you have people who won't cite how they grew the material. And sometimes it's down to the idiosyncrasies of what we published. Sometimes the exact cooling schedule, the exact ratio isn't that tight spec, but when it's reproduced from ours digit by digit and then not cited, it's like, come on, we're trying to play by the rules. The quid pro quo is you then cite it. But so there's a culture. Now, maybe it's not so much in chemistry because, physicists often have that's chemistry. Everyone knows that. And that's an arrogance and a problem that physicists need to deal with.
Makes me crazy when it's like, this was made using the method cited in whatever paper. It's like, don't make me go dig down another paper. And oftentimes it doesn't even have a complete set of details.
Oh, no. Then it's buried three more deep. And then it's some guy's thesis. Oh, no. It's funny. I was editing one of my students' papers today where I exactly said that, which is, they made some crystals by solution growth, but then also they reproduced by the technique in reference 9. And, you're going to make me look at that? Come on, write what you did. You may have done something slightly different. Preaching to the choir, but there you go.
So Andrew and I do a lot of coding, right? We do a lot of our stuff is computational, but it's the same thing. It's the exact same thing. There's a guy who has a technique. I'll leave him nameless for the sake of today. But yeah, it's like we asked him, like, dude, this is a really cool technique, like, and he's just like, well, keep it quiet. I've got this really cool thing I'm writing in all my grants. It's like, come on, dude, like. I get it that other people start to use it and it'll quit being your unique thing, but it'll move the field forward. Or in papers, right? I say, like, if you don't provide the data in the code, I can't do this, which means that this is a commercial. You're just telling me you're running an ad about your material. It's not science because I can't reproduce it. Anyway, so I completely hear you there. One thing I like in the paper, Paul, and I'm curious to get your thought on, you have this analogy to food that can sort of exist on a continuum. You say that Indian pilau, European pilaf, Spanish paella, Cajun jambalaya. These, and I see it as you say that, it's like, oh yeah, those all there's differences, but they do exist in this sort of continuum. I was curious because you didn't go into a lot of detail about it, but how that maps over to material synthesis. Is it the structures like the Russell popper can eventually be thought of as sort of like a Dion Jacobson, like that sort of thing, or is it in the synthesis technique? Or I'm curious for you to riff on that a bit.
Sure. There are different ways of exploring phase space. Okay, so one of them is what I would call runs across the series.
Yep.
Okay.
The game of X.
And, well, I'm at Ames Lab. Ames Lab is where Frank Spedding originally figured out how to separate thorium and uranium from the rare earths and then purify all the rare earths, which, by the way, are not rare. They were rare to have in high purity form. But if you can, and one of the reasons for this is the trivalent rare earths are all very similar chemically, so the old chemical tricks of separation didn't work very well. Lovely. What that means, though, is if I can grow Gado XY, I'm on a first name basis with the rare earths, so yeah, gadolinium.
We gotcha.
Yeah, if I can grow Gado XY, I can probably grow terbium or samarium or neodymium or erbium. So you can go across the whole rare series. So for quite a few series where there had been limited characterization data, where chemists of the old school would discover the structure and then move on, we would grow every possible rare earth and then study it. So this is a continuum that you can walk across. It's all the same structure. It's rare earth XY, but lanthanum XY is really different from Gado XY, and Gado XY is Heisenberg by definition. Terbium XY might be Ising. So you can get different physics, different aspects that way. Now, that's basically going across a very friendly row. You also can move up and down columns. And that's sort of one of the other things you were suggesting. So when we were looking at barium iron 2 arsenic 2, we would do substitutions. We ended up being able to substitute cobalt and nickel, and then we could do rhodium, ruthenium, palladium, and then we could move down to osmium, iridium, platinum, and just sort of see what's going on. Those were very interesting exercises in, is it band filling, is it sterics, is it size of a fluctuating moment, etc. Now, having done all of this to, again, point out that, look, new material space is a equilateral triangle where you've got solid state chemistry, solid state physics, and metallurgy. Great. I'm sort of in the middle, but I'm a bit more toward the physics, closer to chemistry than metallurgy, but sitting there. Fine. I work with physicists, and sometimes physicists, I've heard they can be arrogant. I've never,
No.
I don't know. No.
I've never heard that one.
Exactly. So I had a colleague who, he's an experimentalist in solid state physics. And he said, look, you've moved all around. You've tried to put in chromium and cobalt and nickel, ruthenium, rhodium in these barium iron 2 arsenic. Why don't you put in the element above iron? You've gone everywhere else. Why don't you go to the element above iron? And it's like, what are you talking about? I mean, he did not appreciate that there was no 2D shell, I guess.
First row transition metal for a reason.
Exactly. Yeah. But I'm sure you have chemists who, when I play with chemists, sometimes
for sure the converse. For sure.
Explaining them the basics of measurements or whatever. Whatever. I think I went off on a tangent. Sorry.
Well, no, I love it. Let me zoom out for a second and say, if my takeaway from this first paper is that just like you can learn to be a good cook by being trained by a good cook, by following recipes, by developing intuition, that's one way to develop new materials. If I pivot to look at your other paper, it's a totally different approach. The next paper you sent us is this Hash House Harriers, the winding path to materials discovery. To set people up on this one.
Did you do reading about the Hash House Harriers?
Well, I didn't know what it was. I started reading this, and you have a paragraph where you allude to it, that there's this weird symbols on the ground, and they're sort of following clues, and they're screaming.
They
and I had
call
to Google
themselves
this.
a drinking club with a jogging problem.
Yeah, tell us about this, and then how it relates to materials.
Right. Well, I ran into them when I was a undergraduate at University of Virginia. You would have behind the freshman dorms, you have Observatory Hill, which is a nice path you can walk around. And often on Friday afternoons, you would hear on, and then you would see sort of people running around, and you'd see cryptic white powder markings on the road, which turn out to be flour. And finally, you see a bunch of sweaty folks gathered around a keg of beer. And what it is I think it comes from British Empire originally, but it's a group of people who decide to have a guided random walk through phase space with the goal of A, getting some miles in, B, just catching up with mates, and C, getting to that damn keg of beer. What happens is someone lays the trail. So I can't remember if it's X's or O's, but there are false trails, and then they end, and then someone else finds the right lead and says on, and it sort of goes amoeba-like over the countryside. And it's not that far of a stretch to say, hey, this is what research is, because you have various groups all over the world trying to find something. And when they do a publication, it's either on or, this was a dead end. And, slowly you make your way through phase space. And again, it's ideally a social activity.
I love that
we are.
You point out that, so you say here, for the Harriers, selecting the right shoes for a particular jog is a precondition for some treks. And it's like you're tying that into, the shoes could be a metaphor here for your different synthesis techniques or the family of materials you're sort of looking at. I wonder how often you find yourself as a PI and your group sort of trying to guide your students versus letting them discover trails that you might have missed otherwise in this sort of analogy. Because ultimately, right, you just want to be open
that's your
to
ideal
discovery.
Student.
Yeah.
No. As long as there are no injuries.
Follow the curiosity.
Well, no. I mean, we'll tell you what, at some point we need to do have our game of eat, wear, or kill. You remember that. But you have to be careful. So as long as the ideal student pursues a interesting idea that doesn't cause damage to themselves or the lab, that's great. Part of it is teaching the aesthetics to people. Part of it is, sometimes you just need to use a different tool or idea or technique. So, over the decades, we've assembled a fair amount of different synthetic techniques. Solution growth is my favorite, but of course we can do solid-state reactions. We arc melt, vapor phase transport. We have the ability to do high pressure, high temperature synthesis. I've got colleagues across the street who really like Bridgman and Czochralski and zone refining. It really depends, but my lens on it is I'm interested in making the material so as to interview it. And to interview it, you make a measurement, you ask questions. In the same way as I'm interested in cooking so that I can enjoy eating or share it with other people to eat. There are people who are crystal growers. And for them, it's really figuring out the technique of getting bigger, better, nicer, whatever. That's nice, but it's the same way there are people who make knives. That's good, but I just want to use the knife to do something. I want to use the crystal growth to make the material and do the measurement.
I think another thing that stuck out to me in your paper is you talked a little bit about how unpredictable discovery can be, but how there are still some heuristics and guiding principles towards that as well. And it makes me think of that one quote from Louis Pasteur that fortune favors the prepared mind. And in some ways, you don't necessarily always know what material you're going to find or that you are going to discover something new, but making key observations and knowing the telltale signs that there is something interesting. Doing that,
Oh, absolutely.
I can tell just from our ongoing dialogue, you put a lot of emphasis on observation and careful observation of results. And I wonder if you can talk a little bit about what role careful observation has played in finding materials in places where you didn't think you would.
Okay. Bring me back to the subtle. I'll do the obvious first, okay? Obvious. New growth. Had some undergrads for summer wanted to give them a growth that was potentially interesting and non-fatal. So it was scandium zinc. No. You're not going to start an undergrad on arsenic or phosphorus. But they decanted, and I said, look, after you decant, separate the extra liquid from the solid. I wanted to come look. And I looked at it, and it was as simple as counting. 1, 2, 3, 4, 5. 5. The facet was a pentagon.
That's different.
Oh, quasicrystal right away. So, I mean, just observation of looking at it. So, I don't have X-ray eyes, but I had worked enough with quasicrystals to realize that we had discovered a unprecedented, new, stable, binary family of quasicrystals. So, yes, I was prepared. I had spent a couple decades every now and then visiting quasicrystal land, and therefore it was clear. And that's what dragged, I keep trying to leave the business, but they keep dragging me back in. I was trying to grow larger single crystals of a ytterbium-based heavy fermion material, and the son of a gun nucleates all over the place. And therefore, I get lots of tiny crystals instead of the one big honker that I wanted. Except one growth was different. And I had put in a batch of 6 because I was playing a numbers game. I put in 6 different growths, different parts of the furnace, trying to see if gradients,
same composition, same inputs, just different regions.
Yeah, no, because look, nucleation. Sure, if you're not controlling nucleation, it's a crap shot. You buy lottery tickets. And one of them was really, really, really different. And I struggled to reproduce it. And I then thought, oh, God, that was ampule number 4. Ampule number 4 was the one where I was using the leftover pieces of ytterbium from the last ampule, all the little tittles and bits. And then the other ones were larger ones. And I suddenly realized, oh God, if my ytterbium is as a solid dispersed around, probably when it melts, it doesn't burn the crucible as badly and therefore provide nucleation sites. And therefore I started cutting up the ytterbium into little bits, trying to mix it a bit more so as it melts first, ytterbium's a low melter, it doesn't have sort of microthermite reactions with my alumina crucible. But, these are irritating details. But if you don't pay attention to them, they'll continue to be irritating. Yep. There was a professor of mine at UCLA, Seth Putterman. He was a theorist, nonlinear hydrodynamics, solitons, stuff like this. And absolute, a theorist when I was at UCLA. But a number of years after that, he got very interested in sonoluminescence, which is you can put transducers on a flask of water and drive it, and you can get cavitation. And if there's high enough symmetry, it can collapse and you can get emissions of really high energy photons. So it's an energy amplification. And Seth got really into that. He, spherical flasks, transducers, and I bumped into him, 15 years postgraduate. And he said to me, my God, I never realized how easy theorists, and that includes computational guys, how easy theorists have it, because they only need to know the Hamiltonian. Experimentalists need to know the Hamiltonian, but they need to know what's the right glue and what the impurities in the metal are and all of this stuff. So, there are all these irritating experimental details, which is why right now all the experimentalists at Ames Lab are all volunteering a couple weeks of their time. We're doing a 2-semester course called Experimental Methods in Condensed Matter Physics. We have solid-state chemists, metallurgists, physicists, and it's really, 1, 2, 3 weeks of just going over irritating experimental details of all of these different growths and what they allow you to do. And inevitably, this is the course where people tell me, oh, I'm stealing the slides, I'm using it for this presentation, that presentation. It's useful.
Yeah, these bits of sort of micro knowledge like that don't get passed on otherwise.
Yeah, absolutely.
So,
all right, yeah. So
my takeaway from the first two papers, right? The first one is buy a cookbook, get a mentor, right? Go to cooking school, and you can find new materials, and you develop an intuition. But that takes a lot of time. Your second paper is sort of be open to observations, right? Follow the right paths. Have an open mind, and you'll see what you discover. So those
enjoy the journey.
Learn to enjoy to jog. Yeah, absolutely.
Yeah.
Those are both good techniques, and I think that's what's been used for a long time with materials discovery. Sort of like serendipitous, we come across something, right? You point out, the neodymium magnets, for example, turned out apocryphally, right? And who knows if it's true, but a little bit of boron from the boron carbide crucible gets in there, and all of a sudden we have these magnets. Maybe it wasn't necessarily
nitride.
Was it boron nitride?
Yes, sir.
Excuse me. In any case, so if we shift gears to your next paper, it's about fishing is the analogy here. But what I like about it is you start to play the probability game, right? Just like, I can throw a fishing line anywhere in the river and who knows, like maybe a fish will bite. But if I have learned a little bit, I can increase my odds, right? If you know a bit about fishing, you know that they love to sit behind like the big log in the water. They like to find the shady bank. They like to be right after the rapids, right? There's spots where you can find them. And that is essentially what you're comparing to the process of learning materials design. You have this quote, which I'm going to cite here. It says, to this end, design is an attempt to use a combination of theory and intuition to shave the dice while playing craps with nature. You're still, like you said, just barely, like it's still a statistical game, nucleating the scene, for example, but you're playing the game into your favor a little bit. You're improving it a little bit by understanding through materials design where you're more likely to get some hits. You want to talk a bit about that?
Absolutely, because I am riffing off of Einstein's quote and inverting it.
Yeah.
God does not play dice with nature. Well, I'm playing dice with nature, and I'm trying to shave the dice. We can use what we have. I think maybe even at talk at the Gordon conference you were at, I ended with 2 examples of shaving dice. Look, there are trivial ways. Okay, so let's start with trivial. If your best friend does NMR and you really want to just feed your best friend, then you need to try to make materials that have good NMR nuclei. Your friend will love you if you focus on phosphorus and boron. Okay, if your colleague down the hall is a neutron scatterer, he will not love you if you use gadolinium, europium, or boron 10, but he'll be happy with boron 11 and other rare earths. Okay, so there are certain measurements that require certain elements, but that's a rather trivial way. Let's say you're interested in looking at a classical Ising system. Okay, and for me, classical Ising is something that has a moment that's either pointing up or down, north or south. Okay, so if it's a tetragonal crystal along the z-axis, I can shave the dice very well there by by looking at a rare earth series. I can grow the terbium TB versions and see whether I get axial or planar anisotropy. Depending on which, I can continue looking in the neighborhood of terbium, or I can jump over to erbium or holmium or thulium, because you have a change in the sign of the B20 term, which lets you figure out what the anisotropy is. That will be a quick way to try to identify the most Ising-like in a given series. Those are more individual ones. Let me give the 2 broader ones, and I'll get to your favorite one at the end. I'll just keep you waiting. So fishing holes, okay? If you think of a binary phase diagram is a compilation of humanity's knowledge about 2 elements. So we can have A and B and temperature. Often, binary phase diagram, any phase diagram, is a suggestion of reality. It's sort of our best estimate at the time. They change over the decades. They still change. I've had to correct several over the years, and I take umbrage at that. That's not my job. But, you just find out that this is how it goes. But in a binary phase diagram, you'll often have, in some of them, a eutectics. A eutectic is a minimum in the single-phase liquid region. It occurs generally at a point, which is a given composition, a given temperature. Now, you can have deep eutectics, and by that I mean you can have a mixture of 2 elements be in a single-phase liquid at temperatures way below the melting point of either element. Well, if you're interested in growing materials out of solution, which I am, such a deep eutectic is a fishing hole.
Yeah.
It's telling you these 2 love to mix, and therefore you have the possibility of adding some 3rd or 4th element and growing something. So it is literally a place you can drop your line. Okay? Now, what I've been looking at recently, so if everyone knows about a fishing hole, it's probably pretty well fished. It's that secret fishing. It's that hard to get to fishing. And as we said, I don't like secrets, and that's not to my benefit in a professional sense in a dog-eat-dog world, but I'm more interested in humanity than some of the dogs. Okay? That said, some fishing holes are hard to get to. So we've realized recently that we can take pairs of elements that are really incompatible in their demands. You have materials that are called refractory, and that's just a fancy word for they melt at really high temperatures. And you can have other elements that are volatile, and that just means that at some temperature you're concerned about, they have a large partial pressure, okay, or the boil or whatever. So manganese and phosphorus, cobalt and phosphorus, palladium and phosphorus, or sulfur, or selenium, any of those guys. You can take your favorite transition metal, which most of them melt at really high temperatures, and you can take volatiles. And it turns out that for many of these, you have eutectics close, and rather deep ones, close to the transition metal. So if you're interested in the physics of magnetism, okay, you can look at your favorite 3D transition metal, and you can say, well, probably people have not explored that much mixing cobalt and phosphorus, or iron and phosphorus, or manganese and phosphorus, at least in the traditional senses of arc melting, or trying to get a synthesis that doesn't take advantage of the fact that you have this eutectic. So what we found is, if you can bring the two elements into the single-phase liquid, which usually involves mixing either powder or small pieces of the refractory and the volatile, heat them up slowly, let them combine into this eutectic, then there's virtually no vapor pressure above the eutectic. Okay? Now, if you want to understand that, you have your refractory on one side, and usually, since it's a eutectic, you have some other compound that has high melting on the other side, and that compound doesn't have a high vapor pressure. The vapor pressure for the refractory is way off to the off stage, right? So these then become very useful solutions to try to discover new transition metal-rich volatile X compounds. And in many cases, these have not been explored systematically. And that's one of the ways we're discovering new materials that either are ferromagnets above room temperature, so they can be practical ferromagnets, or if that doesn't work, sometimes we end up with materials that have a reduced transition metal magnetism, oftentimes very small magnetic ordering, and these are materials that we can bring to quantum criticality, especially if they're antiferromagnets, and perhaps discover new high-temperature superconductors, new exotic states, etc. Now, one thing, I'll talk about shaving the dice again in a moment, but one thing that we haven't talked about, and it's hiding in all of these papers, but I don't think you really pulled it out, and it's sort of important. I have lived a rather blessed research life in that Ames Lab has allowed me to have diverse research interests. And that's important because it allows you to respond to a variety of different results. So I'm interested in practical ferromagnets with less rare earth. Those might help with the energy crisis, new electric economy, etc. I'm interested in quantum criticality, which is being a voyeur at the birth of magnetism, and sometimes superconductivity shows up to cheer. I'm interested in metamagnetic transitions. I'm interested in topological materials, metal insulator transitions that may or may not be useful. All of this is the result of Department of Energy, Basic Energy Sciences supporting broad basic research. And I have a few patents. I do applied things, sometimes by intent, sometimes by accident. But having a broad research interest allows you to pursue what you discover. If you have a very focused applied one, it's, nope, that's not a thermoelectric, that's not a thermoelectric, that's not a and you throw out a whole bunch of stuff that might be really interesting.
You know what breaks my heart is, well, no, on that thought, like it breaks my heart that funding agencies and the people that are complicit is really the reviewers will shoot down someone because they say, oh, that's not their area. It's like, yeah, but you're closing the door to overlapping fields, which is where the most interesting stuff happens, at these junctions of different things. And they'll say, well, Professor X they've never worked in medical devices before, so therefore they can't do anything here.
The reason I wrote Fishing the Fermi Sea is because I got really tired of being told, oh, that's just a fishing trip.
Yeah.
and using it pejoratively. So, no, I wanted to reclaim the word. Sometimes, I think any grant has a degree of hidden fishing. I just want to have it explicit. Sometimes exploration is really important. Another term that is used pejoratively is, that's just Edisonian approach. Yeah, Edisonian approach has its place. Until you and the gods of computation can actually do what you promise, which is do everything in silica, until that point, the monkeys have to use the Edisonian approach. Now, it's guided. You're not trying everything.
Well, and as
now,
I was reading your paper,
for those of you without a camera, you might notice our host has turned beet red.
Well, as you say that, I was reading your paper and something jumped out at me. Like, you're giving this example of this praseodymium indium tin material, right? And in your process,
praseodymium.
Excuse me.
Oh yes,
I'm not on first name basis always.
You need to be formal. So praseo, right?
But I was gonna say, you tip your cards a little bit and show us how you're working, right? You say this. You say, this aim again led by necessity to large unit cell compounds, and you say by looking at a list of known intermetallic compounds grouped by unit cell symmetry and size, and you go on to say that led you. And I hear that and I think that's machine learning. This guy's a machine learner, right? He's a statistician. All you're doing is what humans do. Like,
I'm
we learn
HI.
from examples.
I'm
right?
HI. HI.
Yeah, you're HI, but it's the same principle.
I am HI.
But I love that because it's the same thing that the way that I approach a problem would be the exact same. I would just use a different set of tools to tackle it.
Sure. And one of the things that both entertains and frightens me is the AI/ML. People say, what we really want is to recreate you. So we want you to teach our machines. And part of that, sure, I can try to outline the algorithms or whatever, but I'm still waiting. So let me talk about the other dice shaving, and then we'll get to your AI and other things, because I know you want. But the other
really quickly before we leave this thread, you said it's so great that you are able to work in like 5-6 different areas, so that if one person grows material, another group member basically can say like, that might be useful for this. But elsewhere in the paper, you say how important it is to work in teams and networks of collaborators, which is essentially doing the same thing. If you have friends and you've got a sample, you already measured what you wanted out of it, give it to a friend, let them measure it, sort of thing. You never know what you're going to sort of find that way. I read a book recently on business strategy written by one of my mentors, and he talks about flexible companies. They'll come. You have to have a strategy, like how you're going to go to market, right? You have your predetermined strategy, but the best companies are open to what he calls emergent strategies, right? When a business opportunity comes along, they can pivot quickly. This is kind of that same idea. You have a new material, you have something, and you have the ability to pivot and follow a new thread of physics.
Oh no, and DOE has been good about that, because they encourage and they allow intellectual triage.
Intellectual triage, yeah.
Oh yeah, no, in the sense that if a bomb goes out, you need to do triage. Okay, so when MGB2 happened, I was funded to be looking at this, that, and the other. Fine, doesn't matter. Everything out of the oven. We're going to figure out how to do this. And we did it, and we owned MGB2. PRL a week for 3 weeks. Holy God, it was like surfing a tsunami. It was fun. Same with the iron arsenides. Okay, and that's good. Now, you can't. I think my funding agency would sort of question if I suddenly said, tapeworm. Tapeworm is a problem. Everyone, let's study tapeworm. Okay, probably that's where they draw the line. But on the other hand, it is basic energy research, and there are multiple types of phase transitions, phenomenon, whatever. So in DOE speak, I am the leader of a FWP, which is a field work project, which is a collection of scientists here looking at sort of a large overarching problem. The FWP I'm head of is called Complex States, which is short for complex materials with superconducting and interesting properties. We have a broad focus. We can look at a wide range of different materials and states, and that's what allows us to be productive. So it is, we have to do good science. We have to review well. DOE inspects us and reviews us very seriously. It's not free money by any stretch, but it's nice that there's a sense that broad question basic research is important. So it's been a blessed research career because I've been able to broadly look at a wide range of different materials. And sometimes the material, look, I think I make this analogy. When you discover a new material, it's like having to make a choice with a mistress. Okay? The mistress will make demands. Measure this, do that, I'm this. And you need to decide whether you're going to follow the mistress or say, nope, not for me. So, you do a few measurements. Are you a superconductor? No. Are you a magnet? No. Whatever. You interview, and then you decide whether this is going to be worth your effort in pursuing. Yeah. Other way of shaving the dice?
Let's hear it.
Yes?
Absolutely.
Yeah, well, it's the one antagonistic pairs. It's the opposite of the deep eutectic. So if you have a binary phase diagram, A, B, and temperature, a deep eutectic, you have the single phase liquid coming down, there are some elements that are oil and water. And I think a lot of people, even solid state chemists and physicists, are surprised by this, that, you can have a cobalt and lead, and they will not mix for love or money. So if you look at the phase diagram, it's just one huge dome of immiscibility because people didn't go to obscenely high temperatures to get above it or watch them boil. Now, for years, I would just sort of turn the page because, look, I'm looking for a solution to grow things out of. There's no solution here. And then I ended up asking myself a question. And the question was, well, I wonder if any ternaries exist. And when you look at ternary intermetallics, and by intermetallic, I mean not oxides with well-defined bonding angle rules, okay? There are very few. So the answer is some exist, but very few. And then I realized if A and B are immiscible, I can make an ABC ternary with whatever subscripts nature gives me. But C comes in and separates them. So not only do these elements not want to mix in the liquid, they don't want to be adjacent in the solid either. So C comes in as a NATO peacekeeper. Now, the way you can segregate is you can encapsulate A and have it zero-dimensional. You can sheath it so it becomes one-dimensional, or you can separate in planes and it's two-dimensional. So this realization was a way of dialing in dimensionality, and I have known no synthesis algorithm that as reliably dials in dimensionality.
As just miscibility, essentially. Immiscibility, excuse me.
But in the solid.
Yeah.
So I understand the immiscibility, but it carries. So as a solid state physicist, crystal structure sort of absolves all sins. You get different, minimum free energy, things work. But this hatred, A and B don't want to be next to each other. I suspect it actually, if we were to do pair distribution function scattering in the melt, we would see that we have clusters of C and A and C and B, but no A and B even. But this is a way of dialing it in, and a few compounds, so I look at known compounds, they're generally following. This is the few that exist, but we've used it as a way of discovering new compounds and actually often new crystal structures, which then have low dimensionality. So this is fascinating. And it's, again, low dimensionality is interesting because it often allows you to preserve, for example, magnetism to lower dilutions with transition metals with fragile moments. It's a way of seeing, trying to devise compounds that might host electronic structural instabilities, density waves. Metal insulator transitions is a way of possibly finding materials that could be driven to superconductivity. So it's very entertaining. And again, as a design mechanism, it's new. I'm a physicist, so I ended up talking to a bunch of my solid-state chemist friends, and none of them had heard of this idea or had realized this idea. So it's sort of neat. I'm having fun with it. But it's another way of shaving the dice. I want low-dimensional magnetism. Well, this is a way of possibly finding new materials that manifest it.
On a similar note, here you're adding another dimension to try to destabilize or stabilize a compound. And we know that phase diagrams can also exist under different magnetic fields or electric fields. Do you think current phase diagrams are high dimensional enough? Or do you think adding additional dimensions like this are another alternative routes for discovery?
And on that note,
they
do we
are,
have
but-
the ability to accurately even generate those diagrams?
Well, so let me address both of them. First, the first one, I agree completely, but tragically, you chose the two wrong parameters. Okay, no, because magnetic field is a very weak knob.
But pressure, right? Pressure would be important.
There you go. Pressure. Just think about it. Diamond.
Yeah.
Diamond is not your stable form, but you can form it in Earth's crust. You bring it up quick enough, cool enough, it stays put. I don't know if you're familiar with the phenomenal work that Mikhail Eremets had been doing. He tragically just passed away a few months ago. But over the past decade, he had discovered new classes of materials called superhydrides. So a lot of chemists are excited about these just from chemistry. You can react incredibly hydrogen-rich combinations of binaries or ternaries under gigapascal, hundreds of gigapascal. So you can get to, again, it depends on your lab. So 2 gigapascal, you can buy off the shelf piston cylinder. A Bridgman anvil with tungsten carbide can get you to 10 gigapascal. Diamonds simply can get you to 50. Getting to above 100 is hard. Eremets was getting above 200, 250. Okay, so you can create things like lanthanum hydrogen 10 or 12. And these redefine bonding angles, whatever. But on top of it, these things superconduct at 150, 250, 270. You're starting to get within spitting distance of, if not room temperature superconductor, at least barn temperature for Iowa and winter. And this is phenomenal. So one of the things I'm very excited about, and again, it's sort of fishing holes, but this is a tough one to hike to, is humanity knows most of the ambient pressure binary phase diagrams. It turns out it doesn't need a lot of pressure. I've been able to grow and play with some materials that even 3 GPa, 30,000 atmospheres, okay, can stabilize new structures. And 3 GPa is low, so you have a really sporting chance of bringing it back metastable. And this is really neat. Computation is trying to master this. I think it's getting close, but I think that's a phase space that's exceptionally promising, because if we're thinking practical, if we want it to be useful, then having it exist in a metastable state, the same way diamond is metastable, is sort of important. And I think, 3, 6, maybe even 10 GPa, there are a lot of undiscovered phases. If I told you, hey, here's a binary no one's done anything here. You'd go, what type of binary is that? I want to explore. Well, everything is new again. So I think there'll be interesting things.
So we talked to Jason Corey at ASU on our previous quantum materials episode.
Oh,
and I was delighted to learn about their FORCE Center. You must be aware of it.
Yes.
It stands for Facility for Open Research and Compressed Environment. Essentially, it's the United States deciding finally that we need to have the ability to do science at high pressures. Because to my understanding, the little I understand about it, is that we've been really falling behind in this area. I have colleagues that do this in Berlin and other places, and it's been sad to see that we didn't have that capability. So I love that we now have the ability to start exploring these high pressure regions, because I agree with you. I think that it is the Wild West right now. There's some really cool stuff to be done, and it's not like crazy. You're not talking about 20 gigapascals. You can go just a little bit above to find some really interesting, otherwise metastable materials.
Yep. I want to be a little careful. There is a U.S. community. There are groups of us who have been synthesizing things at high pressure, and we've been supported by various agencies. On the other hand, what they're putting together there is more of a user facility and user support. So what's really nice is for these cubic and octahedral anvils, they're selling the material needed to put it together so you don't have to artisanally fabricate it yourself in your lab.
The big deal.
So
there's US Synthetic and Mega Diameter here in Salt Lake City. They've got hundreds of these presses, but each one costs, $4 million. Like, this is not something that easily a PI could do on their own. They are very large presses. These go to very high temperatures.
Those must be really big, because
and they're for synthetic diamond, right? They're going to
the size of a room.
Yeah, they're very large, but they're 20 gigapascals, and they can go up to 2500 C.
All right, yeah, those are monstrous, because the ones I have, the octahedral and cubic, you can, strictly speaking, get those up to about 20 GPa, but then your payload is sort of a cubic millimeter for scientific.
Yeah, that's right.
But no, I think that's the phase space. So if you're talking about what's not discovered, there you are. So one of the myths I want to dispel is, because people will frequently ask, "How did you come up with that idea?" Or in reality, I've had people say, "Oh, you're so lucky to have found that."
Oh yeah, come on.
Yeah, and I have to explain. No, look, the way we find materials is we're not drunk monkeys throwing darts at the periodic table, and it did not come to me in an opium dream. I assume you're familiar with Coleridge's Kubla Khan.
Not actually.
Oh, Coleridge's Kubla Khan is a beautiful poem. In Xanadu did Kubla Khan a stately pleasure dome decree, where Alph the sacred river ran through caverns measureless demand down to a sunless sea. It goes on for a little bit further, but it's published as a fragment, as an unfinished piece. And Coleridge said, "Oh, my manservant woke me from an opium dream, and I never could finish it." I mean, I'm sure this is used by English students all over the globe of why the homework wasn't finished. But, these don't come to us in opium dreams or whatever. They come to us through systematic studies. We have our guided walks through phase space. We try lots of different things. Sometimes things that I grew a decade ago, and I thought, that's not what I want. We have this beautiful room called the sample library, where I have just little jars filled with all of the
good idea.
Tens of thousands of samples. And sometimes a decade later,
I believe it.
That's what we need. So, for example, we have this beautiful article on rhodium bismuth 2. And it's a material that we figured out we wanted to grow recently when we were thinking, okay, we want topologically non-trivial, we want low electronic degeneracy, we would like it cleavable for ARPES, because ARPES is sort of the tool of choice. And those three statements, let me go, okay, that's interesting. So topologically salient, then I want large spin orbit coupling, large Z. I'll go to the largest Z I can get, bismuth. I go bismuth. Okay, good. I go binary. I want it simple, and then I want lowest possible degeneracy. Well, that's triclinic. So bismuth binary triclinic gives me only 2 real hits, an oxide, which I'm not interested in, and rhodium bismuth 2. So having done this exercise with my colleague, I realized, rhodium bismuth 2. I grew that 15 years
familiar.
I grew that 15 years ago as part of my deep paratectic project. It didn't work. So after having this conversation with him at 10 in the morning, by 1 in the afternoon, I go, here's a sample. I bet it cleaves. And it's like the old Star Trek, the original Star Trek with Scotty, never give an estimate that isn't inflated by a factor of 2. So when you do it in less time, you look like the wizard. So being able to discuss a sample in the morning, give it to your colleague in the afternoon. Here it is. Where's your ARPAS data? I want it as quick as I got you the sample.
Where is this library at Ames? Do you have like a room? How do you organize and label it? Like, how is this
absolutely?
Actually work?
And as a matter of fact, I'm starting to go through it now for a variety of other purposes.
That's too cool.
No, this is always a beautiful place. It's a magical place.
Well, NASC is out there this summer. I may have to come.
Sure. I mean, it's a room with cardboard boxes and lots of bottles, but we know how to go through it. Unfortunately, most of the good ones went to the neutron scatterers and are still hot at Oak Ridge. But whatever, we need to wrap.
Yep. Paul, it's been a pleasure. I guess other people are waiting to use the studio. It was as delightful as I knew it would be. Thank you so much for your time. I'll just end on this. I got in material science when somebody explained to me this concept that new materials are out there waiting to be discovered. I have loved this conversation on ways that we can try and discover materials faster and the tips you've offered. Paul, it's been a pleasure. I hope to see you soon. Okay, today's episode is brought to us by the American Ceramic Societies, also known as ACERS, through their Learning Center. Now, the ACERS Learning Center is a really cool thing that is offered. It actually has 20 plus on-demand courses for ceramic and glass science.
Yeah, and their topics cover everything from the fundamentals to research to manufacturing, and they have an additional subset of courses on refractories that's hosted by Orton Ceramics.
Yeah, Orton Ceramics makes sense for refractories, right? They are like your high temperature monitoring source for these materials. One thing I like about this ACERS Learning Center is that it gives you the opportunity to learn from experts, while you can also learn at your own pace because this is on demand. But instead of just leaving you stranded, what's really cool is that you will have access to your instructor throughout this on-demand course. I know this because I've taught some of these courses for them, and students can take the courses, learn from the videos and the additional supplemental content I provide. And then when they have questions or, want to understand how they could apply it to something else, they can contact me and I can provide that sort of back and forth. It's actually a really great way to learn, much better than a typical online video that you're going to find out there.
Yeah, whenever you try to leave a comment in a YouTube video, you
pray for an answer.
You're kind of rolling the dice on whether you're going to get an answer, but this sounds a lot better than that. And even better, you can visit ceramics.org/materialism to learn more and use the code Materialism to get $100 off your next on-demand course registration. So we're giving you a discount.
Can't beat that, man.
The Materialism podcast is also sponsored by Materials Today. You can visit materialstoday.com to stay up to date on the latest happenings in the material science field and read some of the fantastic articles that they've published. You can also head over to elsevier.com to find out more about their journals, books, conferences, and related programs.
And as always, we are so excited to have you guys a part of the show. I just got back from a conference where I met with so many listeners. It is absolutely unreal to be connecting with audience members from around the world. We would love, love, love to hear more feedback on what stuff you guys want to hear. You can find us at materialism.podcast@gmail.com or the @materialismpodcast on Instagram, or pretty much everywhere you want to find us. We are out there and we love hearing feedback on the show. Special thanks to the people who make the music possible for this show, Alphabot and Kolobyte. We appreciate you. And that's it. We will see you guys next time.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world and are bound only by their imaginations in manipulating those materials.